touch sensor matrix. Touch sensor matrix can detect the human finger position. It consists of two groups of electrodes, transmitting electrodes and receiving electrodes. So it's like a combination of a lot of simple touch sensor into a single one. To measure the position, you should apply the potential difference to a pair of electrodes, measure the capacitance, then you apply the potential difference to another pair of electrodes and again measure the capacitance, and repeat this process for each pair of electrodes. Then you compare the capacitance value to the reference values that you have calculated for the open space. And the pair of electrodes where the increase of the capacitance is more prominent should indicate you the finger position. This way you can even detect the multiple touch positions. But I'm going to simulate only the single finger and energize only the single pair of electrodes, just to demonstrate you how to build the model. Okay, let's start QuickField now. In QuickField, I create a new problem. Matrix. Next. Problem type is electrostatics, length units are millimeters, and the model class is three-dimensional import. Finish. Here is the geometry model editor window. There is no model here yet, so the only action available is to import the geometry model from the step file. Here it is. The model is imported. You can recognize here a finger and a sensor. I'm going to assign text labels to geometric objects. Click to select and the face is selected. To select the body, you should click the selected face again. This is finger. Right click, hide. Click to select the face. Click to select the body. This is glass. Hide. Okay, click here, click here. This is the dielectric board. Hide, and these are two layers of dielectric film. I have selected bodies, faces, edges, and vertices. And I'm going to assign label only to the bodies. Film. Okay. Now let's provide physical properties for these labels. Double-click the label name in the tree. The dielectric electric permittivity is 4.3. Film electric permittivity is 2. Glass electric permittivity is 5. And the finger is a conducting object. There is no electric field inside conductor, so there is no need to assign any properties to the conductor. Click OK. And you see the exclamation mark here. This body is excluded from the analysis. Instead, I'm going to assign label to the faces of the finger. So hide all but this. Select, and the body already has the label finger, and I'm going to assign label to the faces. Finger. These are two different labels. If I click this label, the body is selected, and if I click this label, the faces are selected. I'm going to simulate the finger as an insulated conductor. So for the finger faces, I specify floating conductor boundary condition. Okay. Next, I'm going to assign labels to transmitting and receiving electrodes. So unhide all but films. Let's zoom in. Here you can see the traces of transmitting electrodes. To select multiple objects at the same time, hold the Ctrl button pressed. So these are transmitting electrodes, and on the other side are receiving electrodes. Again, hold the Ctrl button pressed to select multiple objects at the same time. Okay, these are receiving electrodes. And I'm going to simulate the case when only one pair of electrodes is energized. So for these electrodes, again, I specify floating conductor. They are conducting, but they are disconnected from the voltage source. And only for the one pair, for example, for this electrode, I will specify -V. And for one of the transmitting electrodes, I will specify the label +V. For the +V, I will assign electric potential of +1 volt, and for -V, I assign electric potential of -1 volt. Okay. Unhide all. In fact, the electric field is distributed not only in the sensor, but also in the air outside. So I need to add the air to our model. So I'm going to enable the background region. And let's adjust the padding. Okay. Click to select the face, click to select the body. This would be the air. The electric permittivity of the air is 1. Now that's all, the geometry model is ready. And before I could start the analysis, I should build the finite element mesh. You do it in 3 steps. First you build the mesh on edges, then you build the mesh on faces, and then you build the mesh in volumes. The mesh is generated, save all problem files, and solve the problem. The problem is solved. Let's take a look at the results. Here you can see the electric potential distribution on the air block faces. Let's hide the air block. And this is the potential distribution on the sensor faces and on the finger. You can see the trace with positive electric potential and the trace with negative electric potential. I'm going to use the cut by plane to look inside. Let's adjust the cut plane position. I want the cut plane to be in the middle of the trace. Okay, and switch on the 2D cross-section window. Let's zoom in. Here you can see the electric potential distribution and isoline plot. But my task is to find the capacitance. The capacitance is the ratio of the stored electric field energy value doubled to the potential difference squared. So I need to calculate the energy in the entire space. So I'm going to unhide all, edit, select all borders, follow the integrals, and here is the stored energy. The capacitance is double this value, divided by the potential difference squared. Potential difference is 2 volts, so divide by 2 and divide by 2 again. Let's put it here, 1.79 picofards. This is with finger. Now, what will be the capacitance without finger in the open air? That I can calculate easily. For the finger, I specify electric permittivity of the air, which is 1. And for the finger faces, I uncheck the floating conductor boundary condition. You can see the 0 mark next to the label name. That means that this label doesn't affect the simulation results. Save all problem files and solve the problem again. The problem is solved. Let's take a look at the results. Again, I'm going to calculate the stored electric field energy, edit select all bodies, integrals, and here is the energy. Let's double this value and divide by the potential difference squared. So this is the capacitance in the open air. 1.56 picofarads. Open air. If you search for the touch sensor matrix on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the resulting pictures, and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.